Welcome to the Planet of Maths channel. In this video, we're going to talk about the Pythagorean Theorem. This is the first part of the topic, so it's the very basics. First, the content of Pythagorean Theorem. In a right triangle, the square of the length of the hypotenuse is equal the sum of the squares of the lengths of the other two sides. That's what Pythagorean Theorem says, but you don't necessarily need to know it. What you need is to be able to use it. If a triangle is right-angled, this beginning tells us that Pythagorean Theorem works only in right-angled triangles. In a situation like this, there must be a right angle in the triangle, then we can use the Pythagorean Theorem. The next part of Pythagorean Theorem tells us we need to find the square of the hypotenuse. The hypotenuse is the longest side in a right-angled triangle. That is the one opposite the right angle. Opposite the right angle, we have the hypotenuse. That is the hypotenuse. The other two sides are the legs. So here is one leg, and here is the other leg. And with Pythagorean Theorem, we always start with the hypotenuse. Here it's letter A, so we have to square A, because it was supposed to be the hypotenuse squared. On the other side, we take the other two sides, so we square the first leg, in this case, x. And to that, we add the other leg also squared, that is c squared. This is the statement of Pythagorean Theorem for this particular triangle. The most important thing to remember is that here, it should be the longest side. Let's practice this in the first task. Here we need to write down the equations resulting from Pythagorean Theorem for our triangles. In example A, we have such a triangle. It's important, it's a right-angled triangle. So if we have a right angle, we locate the hypotenuse opposite the right angle. It's right here. We have to start with the letter h. It is h squared. Here there is addition, and we add the other two sides, namely d and y, but both squared, that is d squared, plus y squared. This is Pythagorean Theorem for this triangle. In example B, we have another triangle, again with a right angle, so we locate the hypotenuse. The hypotenuse, this is the longest side, that is y. So we put y squared, equal sign, and we add the other two sides with squares. This can be d squared plus h squared. If someone were to write these letters h and d in reverse order here, it would of course also be correct. We also have example C in this task. Again, there's a right angle. Opposite the right angle at this place, we have the hypotenuse, and that's the letter A. So we start from a squared equals, for example, y squared plus, we still have x, of course, also squared. In the second task, we have to calculate the lengths of sides marked with unknowns, that is letters. In example A, there's a right triangle. We have 6 and 8, and we have an x. We need to calculate this x. We'll use the Pythagorean Theorem here. We have a right angle, and from the right angle, we go opposite. Here we have the hypotenuse, which is x. We start from this x. X squared equals 6 squared, and to that, we add the other leg, which is 8, also raised to the second power. We make sure that on this side, the lone thing is the hypotenuse. Pythagorean Theorem is written down, but now we need to calculate. Let's start by squaring these two numbers. The square of x remains unchanged, 6 squared. 6 times 6 is 36. Then we add 8 squared, which is 8 times 8, making 64. We squared, so now we can add these numbers together. 36 plus 64 makes 100. Now we need to calculate x itself, not x squared. This square is a bit of a problem here. In this case, we'll do it so that both sides of this equation will be square rooted. It's as if we're applying a square root on both sides of the equality sign. Such a square root we apply here over x squared, and such a square root we apply here over the number 100. On this side, if we have x squared and it's under a square root, then the root and the square cancel each other out, and we're left with just x. And that was the point, for the square to disappear. On this side, we can write the number 100 under the square root. Here we have to think about whether this root can be calculated, or perhaps it can be left as it is. This root can actually be calculated. The square root of 100 is 10. And here ends our example A, x equals 10. Moving to example B. In example B, our triangle looks like this. It also has a right angle, so we can proceed. Opposite the right angle is the hypotenuse, so here we start from this 6. 6 squared equals x squared plus 3 squared. What's longest is on this side. X isn't always on this side. After writing this equality, we square the numbers. We can square 6 to get 36. X squared is not exponentiated, so we just rewrite it, and we exponentiate the 3 squared. 3 times 3 equals 9. Now we don't want the number 9 to be here, so we need to subtract 9 from the both sides of this equality. The positive 9 and the negative 9 cancel each other out, and here we subtract 36 minus 9 and get 27. This equals x squared. And again, we square root both sides of this equation, meaning we apply a square root here and apply a square root here. Let's rewrite the square root of 27 and then think about what to do next. On this side, the applied square root and the square cancel each other out, leaving just x. It turns out that x equals the square root of 27. We can't compute this square root. However, we can do something with it. We can partially square root it. In the number square root of 27, we can take something out of the square root. We can extract a factor. There are some methods for doing this. I'll use the prime factorization method. I'm going to divide the number 27 by prime numbers, starting with 2, but 27 won't divide by 2. 27 is divisible by 3. 27 by 3 is 9. 9 still divides by 3. That is 3. And this 3 is also divisible by 3. I get 1 out of this. Now I can read this root of 27 from these 3's. First, I pair up what I can. I can pair this 3 with that 3. I get a new 3, and this new 3 goes here in front of the square root. What pairs up goes in front of the square root, so the 3 goes in the front, and what doesn't pair up, like this lone 3, goes under the square root. The result of our example is 3 square roots of 3. Example C. We have a right angle in a right triangle, so we can proceed. This time, however, radicals appear on the sides, but this doesn't change the initial situation. At the beginning, you always need to find the right angle. And the hypotenuse needs to be found. Here it's y. We start from this y. The other two sides, in this case roots, should be put in parentheses. The square root of 6 needs to be squared, and then you add the square root of 7 to it. Also enclosed in parentheses and squared. Y squared remains the same, and here we square. The square root and square, they cancel each other out. What we get is just the number under the root, which is 6. Here on a similar principle, the square and the square root cancel each other out, leaving what was underneath, namely 7. We add 6 plus 7, that makes 13. We have y squared, but we don't want to square, so we square root everything, apply a root here and here. On this side, the square and the root cancel each other out, resulting in y. On this side, we write the number 13 under this root. We look at what else could be done, but in this case, nothing can be done. This is the final result. The length of y is the square root of 13. Example D. We have a right triangle. We move opposite the right angle to find the hypotenuse. That's 2 square roots of 7. We need to square this, so it's essential to put it in parentheses. Roots go in parentheses, especially if there's a number in front of the root. So we put that into the brackets and square it. This equals y squared plus this single square root of 3 squared. Roots in parentheses. Now we need to square this, but in the bracket we have two things. So this square needs to work on this 2 and on this root. So here we have an operation like 2 squared times, because there is multiplication here. And this square root of 7, it also needs to be squared. This is just my informal writing. What do we ultimately get from this? We need to square the number 2. Squaring 2 gives us the number 4. And this square root of 7 squared means here the square and the root cancel out, giving the number 7, with multiplication in the middle between these two numbers. 4 times 7 equals y squared. Plus such a square root of 3 squared, we get this number 3 from under the root. Now one needs to multiply 4 by 7, which is 28. Don't want this number 3 to be here, so I subtract 3 from the both side of the equation. These 3's cancel out. It comes out to 25 equals y squared. Now I don't want this square to be here, so I apply the root. I have a root of 25. Also apply a root here. The square and the root cancel out, y comes out. I equals the square root of 25, and this square root of 25 we can calculate. It's just 5, which means y equals 5. And that's all for this video. Thank you for watching, and I invite you to tune in for the next episodes on the Planet of Maths channel.